Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is Compton effect and the derivation of Compton shift. What is Compton effect? Compton effect is the process by which electromagnetic radiation, generally in the form of an X-ray photon or a gamma ray photon, gets scattered by an electron in a material, thereby losing its kinetic energy to the electron and emerging out as a photon of higher wavelength. So the Compton effect is essentially a scattering process, much like the scattering of billiard balls, and therefore it also goes by the name Compton scattering. The schematic diagram of the Compton scattering process is drawn here. We can see that a photon of a certain energy E and momentum P is incident upon an electron and gets scattered with a different energy E prime and momentum P prime, and the electron gets scattered in another direction with energy E suffix E and P suffix E to indicate that these are electron, energy and momentum. The electron, which is assumed to be at rest initially, has a rest energy of m suffix E c squared. The photon loses some of its kinetic energy to the electron, and therefore, as per the quantum mechanical relation of the energy of a photon, E is equal to h nu, where nu is the frequency of the incident photon, its momentum P is equal to E over c, because photon is a massless particle. The momentum and energy are connected by this equation, P is equal to E over c. Therefore, this can be written as h nu over c. P is equal to h nu over c. Whereas for the scattered photon, the energy E prime is equal to h nu prime, because it has a different wavelength and therefore different frequency. If lambda prime is the wavelength of the scattered photon, then its frequency can be nu prime. The momentum P prime of the scattered photon is equal to h nu prime over c. The angle by which this photon gets scattered is indicated here as theta, whereas the angle by which the electron gets scattered with respect to the original direction is indicated as phi. Now, some of the kinetic energy of the photon is transferred to the electron. So, the electron, originally assumed to be at rest, starts to move in another direction with an angle phi with respect to the original direction. So, this is the fundamental idea of Compton scattering or Compton effect. Before we venture into a derivation of the Compton effect, it is important to understand a few things. When we say light interacts with matter, there are several processes that come to mind. First is photoelectric effect. Another process that comes to mind is pair production and pair annihilation. How is Compton effect different from these processes? Here also light interacts with matter, in this case particularly electron. In photoelectric effect also we know that when light is incident on a metal surface, electrons are dislodged from the metal surface if the incident light had a minimum frequency called as the threshold frequency that would have sufficient energy for that photon to dislodge the electron from the metal surface, provided this photon energy is greater than the work function of the metal. But we have to understand that the energies involved in these two processes are different. While in a metal surface, free electrons are involved, in the case of Compton scattering, This electron is loosely bound to the atom, to parent atom. The energies generally typically involved in photoelectric effect is in the range of the visible light. That is, the photons that are involved in the process of photoelectric effect are visible photons. So the energies that are required are slightly lower than the energies that are required here. Here, X-ray photons and gamma ray photons are required for Compton effect to take place. That frequency, that is the frequency or wavelength of the X-rays and the gamma rays, are the appropriate frequency for Compton effect to occur. Similarly, in the case of pair production or pair annihilation, the energies of the photons are slightly higher than those that are required for the Compton effect to occur. They are typically what we call as nuclear gamma ray photons are required, and that would result in production of a positron and electron pair on interaction of the light photon with the electron in the atom. The nucleus gets involved in that process and thereby producing a positron electron pair. So though all these processes are interaction of light with matter, specifically interaction of light with electrons, we see that the energies that are required for the photon and the energies of the associated electrons or the atoms are different in these cases. Thus, Compton effect takes place only when photons of appropriate energy, particularly in the energy of the X-rays or the gamma rays, interact with the loosely bound electrons of the atoms in a material. That would result in what is called as the Compton scattering. When we say Compton scattering, the term scattering is a very broad term in physics. It could refer to one of the several different processes in physics. At the macroscopic level, scattering could refer to interaction and collision between large objects. At the microscopic level, scattering could also refer to the interaction between particles and fields. For example, the Coulombic field of the nucleus of an atom. So we see that scattering is a very broad term. When we say scattering, generally two objects that are initially separated by a large distance interact momentarily, and there is some kind of a collision between these two objects, and then after the interaction the original objects remain nearly unchanged and they go their separate ways after the process. Such processes are generally termed as scattering. When we say scattering of light by matter, there are several scattering processes that come to mind. Rayleigh scattering, Mie scattering, Thomson scattering are examples of elastic scattering. On the other hand, Raman scattering and Compton scattering are typical examples of inelastic scattering process. Elastic scattering processes are the ones in which there is no change in the energy of the incident photon. Whereas we see that in Compton scattering, which is inelastic, there is change in the energy of the incident photon. There is a shift in the wavelength of the incident photon, and we are going to derive that shift, which is called as the Compton shift, by the end of this video. Classical mechanics can explain the interaction of radiation with a charged object such as electron, and classical mechanics predicts that there should be no change in the wavelength of this incident radiation, whereas its intensity can reduce. In fact, even in Compton scattering, one would observe a portion of the incident radiation to go unscattered. and this forms the low energy limit. That is, the energy of the photon interacting with the electron is not sufficient to dislodge those electrons that are tightly bound to the atom, and therefore those photons emerge out without any change in their wavelength, and that would be called as the low energy limit of the Compton scattering, which goes by the name Thomson scattering. So the final expression of the shift in the wavelength, which goes by the name Compton shift, is what we are going to derive. And let me just write out that expression so that we know where we are heading to. Lambda prime minus lambda is the difference in the wavelength of the scattered photon to the incident photon, is equal to h, Planck's constant, over m suffix ec, mass of the electron, speed of light, times 1 minus cos theta. This is the final expression we are intending to derive, and this is what we call Compton shift. So we can clearly see that Compton shift is relative to the scattering angle of the photon, theta, and it is independent of the incident wavelength. This is an important factor to note in Compton effect. By the end of this derivation, it will become clear as to what is Compton shift and what is Compton wavelength of the electron. The Compton wavelength of the electron is given by this term at the front of 1 minus cos theta, that is h over mec. H over me times c. This particular factor is called as the Compton wavelength of the electron. With these things in mind, let us proceed to derive the Compton shift. Okay, let us now proceed to derive the Compton shift. I have reduced the size of the schematic diagram and I have drawn only the essential part of it for the further discussion here. We begin by writing the expressions for the energies of the photon and the electron and the momentum as well. And then we are going to use the conservation principles, that is law of conservation of energy and law of conservation of momentum before collision and after collision, and then try to derive the required shift using those arguments. First, we can write conservation of energy. Energy before collision is equal to energy after collision. So here photon and electron are colliding, and whatever energy the photon loses, that has to be gained by the electron, and the overall energy of the system has to be conserved. That is the idea here. So if I say energy before collision, initially the photon has an energy E, which is equal to h nu of course, and momentum p. First let's focus on the energy. Initially the electron has only rest energy, which is mec squared. So on the left hand side I can write E plus me squared, mec squared rather, right? And on the right hand side I can write E prime, which is the energy of the photon, and E, that is the energy of the scattered electron, or the scattering electron, so to say. It is a scatterer here. Now, we can also write based on this equation. Let us call this equation 1, because if we have numbers, it is easy for me to refer to these equations later on in the derivation. So E minus E prime plus ME squared, MEC squared rather, is equal to E. Let me call this equation 2. Okay. Now we can write similar expressions using law of conservation of momentum for the photon and the electron before and after collision. But energy we know is a scalar. So we have only one equation there. But when it comes to momentum, we know that it is a vector quantity, and therefore we have to write vectorial equations. That means this is a two-body problem. One photon, one electron. Only two bodies are involved, two objects are involved. For two-body problem, we need to consider only momentum in a plane. That means only in two dimensions, x and y. We don't have to consider the third dimension in this case, because it is a two-body problem. If it is a three-body problem, we have to then consider the momentum in all the three directions, x, y, and z. But here we have to consider only momentum in x and y directions. So conservation of momentum tells us that momentum before collision is equal to momentum after collision. Before collision, the momentum is here P, of course, which is equal to E over C. We'll come to that later. And initially, the electron has no momentum. It is at rest. It has rest energy but no momentum. So it is at rest. So here, after collision, it has a momentum of P electron, whereas the photon has momentum of P prime. So vectorially we can write this like this. But we have no real use for the vectorial equations as such, because we need quantities, magnitudes, and therefore we have to go for the scalar equivalence of this equation. That is, in specific direction, we need components of these expressions, right? X and Y components. So we have to write x direction and right here initially it is along the x direction. The photon is moving only along the x direction. It has no y component. So I can write here in the x direction P, the momentum of the photon. And the momentum of the electron is obviously 0 initially. On the right side, the x component of this particular vector, in this particular direction we need, there is angle theta between these two vectors, and therefore this component will be cosine component, right? So I will write for this P prime, I will write P prime cos theta, because we can split this vector into y and x components. The angle is with the x component theta, therefore that would be cos component, cos theta there. And for the electron, it would be P cos phi, because the electron also has this direction motion or momentum. The x component is in this direction, the angle is phi there, so it is plus P cos phi. Let us mark this equation as equation 3 here, And then for the y direction, I'll write the equation here. For the y direction, initially the photon has no momentum along the y direction because it is just traveling in straight line along that direction. It has no y component. So on the left side I say it's 0. And electron obviously was at rest initially, so no momentum anyway for x or y directions for the electron. But after scattering, there is a y component here for the photon as well as for the electron. That would be, for the photon it would be p prime sine theta, because the angle is theta, the component is along the positive x y direction, so we can say, and then minus negative y direction here for the electron, so minus pe sine phi. Now we can call this equation 4, right? So we can use these expressions and proceed further in the derivation. Now what I'm going to do is, I'm going to square and add equations 3 and 4. These two equations, if I can square and add, then I can use them in my derivation further. So first let me do some kind of a separation to make this, aligning the thetas and sines, the thetas and phis, let me separate here. I can write here Pe sine phi has a negative sign, so I can take it to the left side to make it positive, is P prime sine theta. And similarly here, I can write Pe cos phi is equal to P minus P prime cos theta. Now you can see that I have mainly 3 equations, because if these are the same actually, right? So I have rewritten it in a different way, but they are only one equation, and then we have 2 more equations. So totally I have 3 equations, but there are 4 unknowns. What are my unknowns here? Theta, phi, E prime and E. These are my unknowns in these equations, right? E is known, the energy of the incident photon. I'm supposed to know it. So E prime, E, theta, phi. These are the unknowns. Now you may ask, what about P prime, P? They are not independent unknowns. They are dependent on the energies already. Because we know that E over C is P. So we know that they are connected. For even electron also we can write similarly an equation connecting the energy and momentum. We know that. So we have 4 unknowns, 3 equations. Therefore, it is not possible to directly solve it as such. So in order to solve this, we have to eliminate a couple of unknowns. We can either decide to eliminate the electron scattering angle and the electron energy, or the photon scattering angle and the photon energy, scattered energy. Either this pair or that pair we have to eliminate. Then only we can solve this. This is just a strategy to solve this, right? There are less number of equations compared to the unknowns, so this is the only way to solve this. So we decide to, let us say, eliminate the electron scattering angle phi and the electron scattered energy E suffix E. In that case, we will have final expressions in terms of these parameters. That's what we are going to do. In order for that to happen, we have to take the phi's on the left side, which we have done, and theta's on the right side in these 2 equations, and then energy of the photon on one side and electron on the other side in the case of the first equation, which we have written as second equation here. Now, as per the strategy, we have aligned up the equations. We can now do the squaring of equations 3 and 4 and adding them up. P squared on the left side, cos squared phi. Here P squared, sin squared phi. If you add it up, sin squared phi plus cos squared phi is 1. Therefore, we get P squared only. The other terms we have, that is P minus P prime cos theta whole squared plus P prime sin theta squared. Now if I expand this, I will write P squared a minus b whole squared, a squared minus 2ab plus b squared plus square of this is this expression here. I am going to now, therefore, since we have used these two equations up, we can get rid of these here so that we can get some space to write the equations further. So I am going to bracket this out for later use maybe, and then let me proceed from here to here. Here again, these two terms can be combined. Cos square theta plus sin square theta will give us 1. So we have P prime squared here as extra term. So I can write P squared is equal to P squared minus 2PB prime cos theta plus P prime squared. Let us call this equation by number for reference, that is 5. Now I can write the relativistic expression for the energy of the electron, because the electron here gets scattered by a photon which is high energetic. So to account for all the possible limits, rather the high energy limit as well as the low energy limit, because we cannot assume that the electron moves slowly. It may, relativity will cover for both the high speed and the low speed limits. So we have to use relativistic expression for the energy of the electron, and EE, therefore I write as square root of PE squared C squared, that is momentum squared speed of light squared, plus ME squared C power 4, which is the square of the rest mass energy. So that will be the total energy of the electron relativistically. It's a relativistic expression. Let me also give a number to this expression, that is 6 here. If I square this up, I would be able to write E squared is equal to P squared C squared plus ME squared C power 4. Again, you can give a number to this as well. Let's call that 7. Now, I have equation 2 where I have EE. I have E squared in equation 7. And then I have a P squared here, and then there are other terms, but this P squared I have already derived as equation 5. So I should be able to substitute for P squared in this equation 5. So I can take 5 and put it here. Similarly, I can square this up, equation 2, and then I will get E squared here. That I will be able to substitute for this here. So let me just square this up here and write separately as equation, let's say 2a or something here. So I have gotten rid of all the other unnecessary equations for the further progression of this derivation, and I have only taken those that are important. This one is the first equation that we wrote, and then we modified it and wrote another equation as the second equation, and then when squaring we are getting E squared is equal to E minus E prime whole squared, that is first term squared, plus the second term was MVC squared in that. So when you square that, that is A squared plus B squared, plus there is another term 2AB term that we have to include. So it is 2E minus E prime whole squared MEC squared 2AB. Right? This becomes the equation 2A here. And this has to be substituted for this E squared. And then for the P squared, we have to substitute this 5 here. And then I'm going to proceed doing that now. So this equation E squared is there 7. On the left side is E squared. So I'm going to just take this whole thing here. So E minus E prime whole squared plus 2 E minus E prime times MEC squared plus ME squared C power 4 on the left side. Right side we have P squared. For P squared we are going to substitute this, so it is going to be P squared minus 2PP prime cos theta plus P prime squared, this whole term, multiplied by this C squared plus ME squared C power 4. We can already see that on the left hand side there is an MEC power 4, and on the right hand side as well, so we can cancel that out. And then this remaining terms we can proceed to expand. This is E minus E prime whole squared, A minus B whole squared, so we can write A squared minus 2AB plus B squared plus this whole term is still there, so I'm going to continue writing that as such, 2E minus E prime MEC squared. On the right hand side we have P squared C squared minus 2P P prime cos theta C squared plus P prime squared C squared. The other term was already cancelled. So this is what we have, and we can clearly see that because of this relation that E is equal to PC, we know that we can write E squared is equal to P squared C squared. So this P squared C squared and this E squared will therefore cancel out. And similarly, this E prime squared and this P prime squared C squared will cancel out. And we are left with the remaining terms, of which minus 2 is present in these two terms, and here it's plus 2. So we can divide the whole thing by minus 2. We can write therefore this equation as E prime. This plus becomes therefore minus, since we divided by minus 2 here and it's already plus sign there. And then on the right hand side we have P prime cos theta C squared. We can proceed to now derive the shift using this. Again, this P and P prime, we can substitute E by C and E prime by C for these two terms. So we do that here. E prime, both would have C 2 times, so it is C squared here, and then cos theta C squared. This C squared and this C squared would cancel out. So what we would essentially have is E prime. We bring this from the right side to the left side, and then take this to the right side, already since we divided by -2, this term won't have any minus there. When we take it to the right side, we would have E minus E prime me c squared. Now here we can take the E prime out from this expression. Then we would write 1 minus cos theta. On the right side we have E minus E prime c squared, of course me c squared. If you divide the whole thing by E prime, we would have one minus cos theta on the left side is equal to E by E prime would be 1 by E prime, and then for the second term it would be 1 by E or 1 over E times MEC squared. Now I will proceed from here. Now I have kept only the last equation for further progression of this derivation. That is 1 minus cos theta is on one side. I have 1 over E prime, which I can write 1 over H nu prime minus 1 over E, I can write 1 over H nu MEC squared. Now if I multiply by H and divide by MEC on the left side, I would have H over MEC 1 minus cos theta on the left side. On the right hand side, when I multiply by H, the denominator H would go off. And then when I divide by MEC square, MEC here MEC squared is there, so this will go, this will go. What we will be left with only C there. Bring that C inside. So I would have C over nu prime minus C over nu. And we know that C is equal to nu lambda. C is equal to nu prime lambda prime. And therefore, C over nu prime is nothing but lambda prime. C over nu is lambda. So we have got lambda prime minus lambda on the right hand side, and then H over MEC 1 minus cos theta on the left hand side, or we can write the final expression, which is the Compton shift. Lambda prime minus lambda is equal to H over MEC 1 minus cos theta. This is the final expression that gives us the Compton shift of the scattered photon. This particular term, that is H over MEC, is called as the Compton wavelength of the electron, which if you substitute Planck's constant, that is 6.63 times 10 power minus 34 joule second approximately, ME, mass of the electron, 9.11 times 10 power minus 31 kilograms, C, speed of light, 3 times 10 power 8 meters per second, you get lambda C, that is the Compton wavelength of the electron, which is a constant, that would be equal to 2.43 picometers, 10 power minus 12 meters. That's a very small number. And because it is such a small number, even when theta is 180 degree in the scattering, that is, even if the photon hits the electron and returns back in the same direction, that is also considered as scattering. That time the angle would be 180 degrees. Cos 180 degrees minus 1 So 1 minus of minus 1, this term would become 1 plus 1, therefore that would be 2. 2 times this is 2 times this lambda c, that is this Compton wavelength of the electron, and that would be around 4.86 picometers if I multiply this by 2, because this 1 minus cos theta becomes 2. If I do that, that would be 4.86 picometers. That would be the maximum shift possible in Compton shift. So in a Compton experiment or the Compton scattering, the maximum shift that is possible for an electron would be 4.86 picometers. 2.43 if theta is 0. That is the unscattered wave. There is no shift. That would be 2.43. That means whatever is the wave that is sent, that would come out. That's the minimum. The maximum is 2 times that. That would be still a small number. Even 4.86, that is twice of this Compton wavelength of the electron, which is the maximum shift possible. Even that is too small a number for other wavelengths such as the visible light or the ultraviolet or other wavelengths to cause any significant shift. That is why we don't observe Compton shift for visible or ultraviolet light. Because for X-rays, the wavelengths are too small such that this picometer values are still considerable. The shift is still considerable. But if you use visible light or ultraviolet light, the shift becomes too small a number because of the Compton wavelength of the electron being so small. And that is the reason we don't see any shift when we use higher wavelength radiations such as ultraviolet or visible light for observing Compton shift. We need essentially either X-ray photons or gamma ray photons for Compton effect to occur. Before we conclude this video, let us briefly discuss Compton's experiment and actual original results that he observed. Compton used an arrangement of this kind. The schematic is shown here. He had an X-ray source from molybdenum, which was used as the target in the X-ray tube, and that produced X-rays of a certain wavelength, K alpha, which was of interest to him. Actually, it produced X-rays of several wavelengths. So, X-rays of different wavelengths first were made to fall on a block of carbon in the form of graphite, and then the emerging rays were collimated properly using something like a lead block with small hole through it, and then they were made to fall on calcite crystal before being analyzed by the detector in the Bragg spectrometer that was used to analyze the radiation. Bragg spectrometer worked on the principle of Bragg diffraction, that is 2d sine theta is equal to n lambda. You might have heard of this very famous equation in physics. So, depending on the angle at which it is scanned here, different wavelengths can be accessed. But of particular interest was the molybdenum K alpha line, which Arthur Compton tried to access, and then see how much is that line getting shifted because of the Compton shift or the Compton scattering. That was an essential idea of this experiment that he was doing. So here, a particular plane, for example, around with a d value around 3 angstroms roughly in calcite crystal, scatters that particular. So this block of carbon in the form of graphite is actually the scatterer, that is providing the electrons that are involved in the Compton scattering process. And therefore, by analyzing the wavelengths, one can get information about how much is the shift. Here we plotted the graphs that was originally obtained by Compton in his experiment. Intensity versus wavelength can be plotted this way. The unscattered is the peak on the left side here in all the three bottom diagrams. The original diagram without any scattering is captured. And when the block of carbon is placed, it starts scattering the X-ray photons and you get a unscattered peak and a peak corresponding to scattered. Similarly here, as well as in the third diagram down below here. Now in these T diagrams we can clearly see that there is a shift compared to the unscattered and the scattered in wavelength, which is the Compton shift, del lambda in our original expression. And this shift increases as the angles were changed, right? The scattering angles here were changed from 0 to, let's say, 45 degrees to 90 degrees to about 135 degrees finally. These were the different angles that were used in his experiment, and then he scanned each time over a small range of wavelengths, because that is how this Bragg diffraction equation works, and therefore he has to scan there. So that wavelength was calculated from the small scanning angle. 2d sin theta is equal to n lambda is the Bragg diffraction formula. In that, if you want to get lambda, you should know some theta there, right? That theta is the scanning angle here that he was using in his Bragg spectrometer. So the actual technical details of this experiment is slightly more complicated than the simple picture that we are trying to present here. But the basic idea is what we discussed in the derivation, that you need a material to scatter the X-ray photons, and then out comes the scattered wavelengths. You should be able to measure and detect these scattered wavelengths, and you should be able to produce curves of this kind, and you will be able to easily see that the Compton shift is proportional to the angle theta, that is the angle by which the photon gets scattered in this experiment. Right, so Compton performed this experiment in 1920s, specifically I think around 1923, and since it was such an important experiment, he received the 1927 Nobel Prize in Physics for his work on scattering of X-rays and gamma ray photons. Arthur Compton in the year 1923 provided a theoretical explanation for the effect that goes by his name, that is the Compton effect. The actual observation of the experimental effect had been originally done by J.A. Gray, which Compton wanted to experimentally verify first and then provide a theoretical explanation, which he did using quantum mechanics. The importance of Compton effect in confirming the quantum theory in general and providing a solid proof to the photon theory of light in particular cannot be overemphasized. That brings us to the conclusion of this video. Hope to catch up with you soon on another interesting video. Until then, it's bye from me. Thank you.